Ladies and gentlemen, boys and girls, welcome to the Hertford Astronomy Group. I'm Alan Willison, and it's my pleasure to welcome you to this meeting. I hope you've all had a lovely day, the sun's shining, and it's been absolutely glorious out there, and that is absolutely wonderful because of our meeting tonight is about the sun. Format of the evening, I've got a few announcements to make at the beginning, and then I'll be passing you over to Martin, who's going to tell you about the night sky. And then Martin will pass over to Jerry, who will introduce tonight's speaker. I must say at this point, our speaker has very kindly said that there's no fee for tonight, but we're going to make a donation to the Macmillan Cancer Care on her behalf. So thank you very much indeed, Helen, for that. We are recording the programme, as you gathered, so if I can ask everyone who's on Zoom if you can mute yourselves and then keep your fingers away from the space bar. Those of you at the university, if you can make sure that your mobile phones are switched off so they don't disturb anybody, and that you adhere to any notices about fire alarms and so on. We're not expecting to practice them tonight, so if it goes off, just follow the direction that you'll see Martin running and meet on the car park, and they will check everybody is safe and sound. Okay, just before we get into the meeting, a couple of dates for your diaries. June 28th, HAGAS have got a meeting about some lovely astrophotography stuff, especially it's all about AI in image processing. Let's hope that's going to be something that's going to make your job even easier. I know you work very hard at it. Maybe AI is going to take some of the strain away. And another date, July the 9th. If you're around on July the 9th, why not come over to the Wheathampstead Village Day, where we're hoping to have set our stand up and tell people all about the Hertford Astronomy Group. Just one more announcement. We spoke about holding the possibility of holding our own convention. Unfortunately, that's not going to be possible. We've looked at it and we've decided it's something we're not going to be able to do that. So we'll cross that one off. Okay, so I think that's enough from me to get things going. I'm now going to pass you over to Martin, who's going to tell us about the night sky. So over to you, Martin.
Okay, so this I found also on the internet the other day, which was quite interesting, about JWST found the first stars in the universe. That's just an artist's impression there you're looking at. But I mean, I'll put a little bit of information there about the elements of hydrogen, helium, and all other elements by astronomers called metals, strangely enough. It's mainly because the majority of atoms in our universe are either hydrogen or helium, mainly hydrogen. So anything else is produced due to stellar interactions where these other elements are produced either through stars or supernova explosions and white dwarfs and neutron stars. So that's quite an interesting image there. Next one, I'll talk a little bit about Ariane Rocket 5, another little bit of information I've gleaned off the internet. So it's approaching readiness for its final liftoff schedule, 16th of June, which is Friday. So the image there of the protective fairing being positioned. So obviously Ariane 5 has been instrumental in a lot of satellite launches recently, and it's also had something to do with the JUICE mission to Jupiter, so I thought that was quite interesting. We've also, Airbus in Stevenage have a lot to do with some of these, so it's a big thing in our industry. We are one of the head countries in aerospace. So this one now I've also come across. Some of you have been in the club a while will know that we've had Damien Peach come and give us talks. He's main thing is imaging the planets in our solar system, and he's been publishing a few of his images, which he's been modifying. I think that's incredible to think that that's been taken from the Earth, picture of Saturn there. I think you'd think it was taken by one of the probes that's gone to Saturn. It's so clear. But hopefully, again, at some point, we'll see if we can get Damon to come back and give us another talk, because he does a very interesting talk. So, looking at the planets in June, it's obviously this is a bad time of year for us. We've got the longest day coming up in a week or so's time, 21st or 22nd, 21st of June there. So we get only a very short period of complete darkness. Not so good for people doing imaging. So some of us turn to solar imaging. We'll look at that in a minute. But we can still see Venus. Venus has been very predominant in the sky is this time of year because it's inside our orbit. And if you look to the west, it's very clear. So that image that I've just shown is due on the 21st, which is the longest day of the crescent moon close to Venus. So again, that's quite nice. But do be careful and make sure the sun has gone down before you do any viewing through binoculars or telescopes close to the sun. So, looking at the little bit of night sky we have, we can look at, and if you're up late in the evening, want to have a look, Cygnus is quite predominant in the east now, and quite easy to spot. Cygnus of Swan looks like a large cross in the sky. And one of the nebulas is actually a supernova remnant, the Val Nebula. And if you follow, I've got a pointer here, and work it. So if you follow these three stars, Vega, Deneb, and Altair, they're the summer triangle. But if you follow a line between Altair and Deneb, you'll find the Val Nebula. It's quite large, but not very bright, I'm afraid. So without a pair of binoculars, or if you're in a dark skies area, you can see it. But what I've actually done is an image I took last year of Val Nebula, just to show you what it looks like. So this was a supernova remnant, and the supernova would have been, can't say exactly where, but somewhere in the centre of the circle of the ring there. So it's actually break it down into separate nebulas. So this is the Western Nebula, this is the Eastern Nebula, and this is Pickering's Triangle here. So the supernova would have been around this area here. But just for inference, it's I put a little bit of information about the actual size of it. So the star would have been 20 times the size of the sun, and exploded approximately 10,000 years ago. It would have been as bright as Venus in the night sky if you were alive at that time. And again, it's about 3 degrees, which is 6 times the diameter of the moon. So it covers a large area. So looking again, another interesting thing to look at this time of year is some of the clusters. We are actually looking out from the Milky Way, if you look at the moment. So in Hercules, we've got M13. So if we find these 4 stars, M13 is in between. It's called the Keystone Asterism. But can be seen quite clearly with a pair of binoculars. It is quite a bright cluster. I'll put a bit of information there about that. You can see it with a telescope or binoculars. In a dark skies area, you might even be able to see it with the naked eye. So I've included an image of it, but not one of mine. This is one taken by NASA that gives you an idea of the cluster itself. Beautiful coloured stars. So you've got blue, gold, and white stars all in there. Nice cluster. A little bit of information there. It's several 100,000 stars. They've been there 12 billion years, so it's quite an old cluster. Some information. Oh yeah, Arabico message. Yeah, this is the information about, they sent a message back in the 1974, containing information about human DNA and what planet we were from. But interesting that the cluster is 25,000 years away, so that means it's going to take 25,000 years for the information to arrive there, and then another 25,000 years for it to come back. So, but just a useless bit of information. Thank Drake and Carl Sagan. So if anybody's watched the old Cosmos series by Carl Sagan, they'll know exactly what I'm talking about. So if you get a chance, go and have a look at that. That is certainly worth a view. Not trying to steal Helen's thunder here, but this was an image that Steve took of the sun. I think this week, did you take it, Steve? This week. So I thought I'd just put a little bit of information in there about solar activity at the moment and the cycles the sun goes through, 11-year cycle. So it's showing quite a few sunspots and predominances there. So Steve put a little bit of information there. He said it's particularly active at the moment. Took this multi-frame high-res composition of the sun with a double-stacked Lunt 80 and quark chromo, blending 16 frames of the solar surface with another 16 of edge-on showing the solar flares. So I think that's a particularly good image. Thank you, Steve. Another image from one of our other astrophotographers, Kevin. This is NGC 7822, which is a star-forming complex located in the constellation of Cephus. It's approximately 3,000 light years away from Earth. A very young cluster of stars. I'll say that, just a bit of information about what's going on in there and the stars that are in it and what's occurring at the moment. So some of these stars are quite hot. This particular one is talking about there. It's almost 45,000 Kelvin. So these are much hotter and brighter stars than our sun. But thank you, Kevin. Brilliant image. Anybody interested in astrophotography, you can come and see me or Steve or Dennis afterwards, and we can show you the sort of things we're doing. And we welcome all, beginners to advance. All are welcome. So this is another. It's an image of mine of the the Crescent Nebula. This is slightly different from supernova remnant because the star this material has come from is a Wolf-Rayet star, which is still not gone into supernova. It's still active. They're unusual stars. They burn much hotter than normal stars, and they shed their material before the end of their lives. So in this particular image, you can see a lot of oxygen, which is the bluey-green color shroud around the outside. But the Wolf-Rayet star is the bright star near the center of that image there. But these have very short life, and it will explode into a supernova in the future. So this star, actually, when I was looking at the image earlier on of Cygnus, where the Cygnus crosses, if you follow the line about halfway down towards the tail of the cross, that's where this particular nebula is. The last image I've got here, the one I've taken of the North American nebula. This particular part of it is called the Cygnus Wall. And this is a star generating area. The Cygnus Wall is about 20 light years across from edge to edge. I've removed the stars to bring the definition of the nebula out a little bit there, just to give you a better feeling of depth. If there's any questions, I'll hand to Jerry to introduce our talker.
Thanks very much, Martin. Another great collection of images, as usual. So here we are at the end of our program for 2022-23. And I can tell you that I already have most of next year's program set up, I'm pleased to say, so there won't be any great rush to do that as we approach the beginning of our new start. So that information will come out to you in due course. But tonight we have Dr. Helen Mason, who's from University of Cambridge and is a solar specialist. I mean, that's an understatement. She has worked on all kinds of solar probes. And in fact, our investigation and understanding of the sun has increased by a huge amount in recent years, with the European Space Agency and NASA sending things like the Parker Solar Probe and others closer to the sun than we have ever done before. In another area of her work, Helen created the Space Sun Art and uses that to inspire school children and others. And in fact, it won the Sir Arthur Clarke Award a couple of years ago. So, Helen, if you'd like to join us, I'm sure we're going to have a quite amazing evening learning more about the sun than we ever have before.
Thank you, Jerry.
Thank you.
Thank you for that very kind introduction. It's a great pleasure for me to be here tonight to hopefully share with you some of the projects that I've been working on, some of the things that I know about the sun. I have worked on the sun, in particular on solar space projects with NASA, ESA, and Japanese space agencies for many, many years, many decades, starting with Skylab, Solar Maximum Mission, SOHO, and more recently with Hinode and Solar Dynamics Observatory, and as Jerry mentioned, Solar Orbiter is now flying. So it's a great pleasure for me to share some of the work that we've been doing. And I'm sure that a lot of you will know some of the things I'm saying, but hopefully there will be some things that you're not aware of. So first of all, this is an image of the sun, and it's taken from the Solar Dynamics Observatory. And you can see over on the right-hand side here, you can see a huge explosion on this coming from the sun. And we'll talk a little bit more about those solar flares and coronal mass ejections a little bit later on. I should have said that I work at the University of Cambridge, at the Department of Applied Maths and Theoretical Physics, and most of this research, all of this research, in fact, has been funded by STFC, the Science Technologies Facilities Council, together with the university. So we've had a golden age of solar space observations. I'm only going to talk about the latest ones. SOHO, that I was very much involved with, was launched in 1995, although we were working on preparations for SOHO well in advance of that. Each spacecraft you launch, you start to work on it probably about a decade before it's actually launched, the individual instruments and the spacecraft. SOHO is still operating, and we're still getting data from SOHO, which is still being used for scientific purposes. Not all of the instruments are still being used, and that's because we have superior instruments. Therefore, we've turned some of them off. But SOHO is, in fact, still operating, amazingly enough. So I will share with you some things about SOHO. TRACE was an ultraviolet instrument which produced some amazing images of the sun. RESI was a hard X-ray instrument, which was used particularly to study solar flares. Hinode, which I worked on, I will share a little bit about that as well. I worked on with the group from Mullard Space Science Laboratory. I think some of you will know Lucy Green, who's from the Mullard Space Science Laboratory, and other people. Louise Hara was the PI on that instrument that I worked with. Stereo, which had 2 satellites looking at the sun to get a 3-dimensional image. Solar Dynamics Observatory, IRIS, which is a spectrometer, Parker Solar Probe, launched in 2018, and Solar Orbiter, launched in 2020. So we don't work alone. When we work on space projects, we work in teams. We work in teams of scientists, engineers, software people, when we work on a particular instrument, all having our different expertise. But this is my team. These are people who are or were in my solar group at Cambridge. And my colleagues here are now professors over in the USA. Giulio Dalzana now leads the group because I actually, believe it or not, retired in 2017, although I don't seem to have noticed yet. Nobody's told me. I'm still doing research and still doing outreach. Yarrow there is in Ondřejov in Czech Republic. Durgesh and Sargam are from India, and we collaborate very closely with our Indian colleagues, and I'm going to talk about that a little bit more. And other colleagues here are in different institutes in the USA. Vanessa on the end was one of my PhD students, now working at Lockheed Martin in the USA. So just some very basic facts to put us in context about the sun. The sun, as you all know, is just a middle-aged star halfway through its lifetime, about 4.5 billion years old. It's our energy source, light source. It gives us life here on Earth. We would not exist without it. It's huge. And here you can see the sunspots that were mentioned a little bit earlier on the sun. And indeed, we're coming up to a very active phase, and I'll talk about that. This sunspot here is about the size of the Earth. So you could fit over 100 Earths across it and 1 million Earths inside it. It's massive, and the surface temperature is around about 6,000 degrees. So if we look at the core, the energy is produced by nuclear fusion in the core, hydrogen turning into helium. So most of the composition of the sun is hydrogen and helium, but it does have trace elements of many other elements, oxygen, carbon, neon, iron, many other elements. So although the temperature in the core is 15 million, the energy is transported out through a radiative zone and then beneath the surface by a convective zone. And the surface temperature is around, as I said, around about 6,000 degrees. Now I'm going to talk mainly about space observations, but I really wanted to start with these fantastic observations from our latest solar telescope based in Hawaii called DKIST. That's what we call it. And here you can see convection cells on the surface of the sun. So this is the highest resolution observations that we've been able to obtain from this amazing telescope. The first light was in 2019, and it's going to have various different instruments that are being developed. But please do look it up. You'll see some amazing images. Also, I should have put in amazing images of sunspots as well, which I should have included. But I'm going to go back in time now, and I'm going back to Galileo, who was one of the first scientists, astronomers, to study the sun and obviously project an image of the sun. As we remind everybody, never look at the sun, use a special telescope, or you project an image. And he projected an image of the sun, and these are his actual drawings made into an animation. And he was able to show that the sun is spinning. It takes about 25 days to spin around at the equator and about 30 days in the polar regions. Of course, he got into trouble again. He was already in trouble because of his observations of the moons of the other planets, because of him confirming what Copernicus had said about the sun being the center of the solar system, when everybody else believed that the Earth should be the center of everything. But he was in trouble again because he said these spots were actually on the sun, and astronomical bodies were supposed to be perfect. So this is a view from his house in Arcetri, in Tuscany. It's owned by the Arcetri Observatory there, and a view from his window, a beautiful village where he was kept under house arrest, a little bit like our lockdowns recently, I suppose, except, you know, when you begin to feel a little bit sorry for him, he had a full cellar of Italian wine. Remember that, okay, so perhaps not quite as bad as it might sound. So we know that these sunspots are one measure of solar activity. There are other measures that we can use, but they're one really quite accurate measure. So the sun goes through a phase of activity, an 11-year phase of activity, from having virtually no, in fact, no sunspots, to having a lot of sunspots. And at the moment, it's got quite a few sunspots. It's on the rise. These are a signal of magnetic activity. These are regions where the magnetic field is very strong and is popping out of the sun. I'll discuss a little bit later. But when we have a lot of sunspots, that's when we have a lot of activity on the sun, and that's when we get a lot of solar flares and ejections of material. And of course, these impinge on the Earth's environment, giving us the northern lights, aurora borealis or aurora australis. Did anybody happen to see the northern lights a couple of months ago? Yeah? Oh, you saw them in the north, but they did come down quite low. In fact, they came to Oxford and Cambridge. I wasn't here at the time, I was overseas, but I just wondered if anybody had spotted them. You needed to be in a dark area, I think. But I've never seen the northern lights. It's on my bucket list, and it's something I really would love to see because they are amazing. So if we look at this is year along the bottom from 1900 up to 2000, we see the sunspot count, the number of sunspots going up and down with an 11-year cycle. And sunspots have been recorded way back in time, from the time of Galileo, also other places like the observatory in Greenwich. People have counted these sunspot numbers. So why do they go up and down like this? Well, it's believed that the magnetic field is formed beneath the surface of the sun. You've got a sort of dynamo effect, you've got a moving ionized plasma, and it's producing the magnetic field in the region between the radiative zone and the convection zone, which they call the tachocline. That's thought to be where it's formed. So if you imagine it's formed in this sort of way, but since the sun is spinning and it's spinning faster at the equator than it is at the poles, it actually gets twisted round. So 25 days at the equator, 30 days at the poles. It gets twisted round like a ball of string and rises up through the convective zone and eventually pops out through the surface. And when it pops out through the surface, it has these large loop-like structures, which I'll show you, and these are where the sunspots are. And then it dissipates as magnetic reconnection takes place, and it dissipates into space. So let me introduce you to one of my other favorite astronomers, who's renowned for his work, obviously, on gravity, his mathematics, and he built his own telescope, a reflecting telescope using mirrors, because with the lenses you tended to get these aberrations of color. And he was very interested to find out what was causing these aberrations of color when he used a reflecting telescope. So he studied the nature of light. People knew that if you put white light, as we call it, visible light through a prism, it would split into the colors. But he then took one of these colors and put it back through the prism, and it stayed that color. So it wasn't the prism itself that was changing the nature of light. He didn't get it completely right, I have to say, because there was a lot of discussion about the nature of light, and was it waves or was it particles? And there was a lot of discussion between him and Huygens and other people. But he got the general concept right. So we can do something even better than just splitting the light with a prism. We can use a spectrometer, and probably some of you are familiar with this, hopefully. If we use a slit, if we pass the emission, if we've got to pass the spectrum through a hot gas, then we will get absorption lines, we'll get dark lines where the atoms actually absorb some light. But if we have a hot gas and we look at the spectrum that comes from that hot gas, then we'll get emission lines. So this is a very powerful way of not just splitting the light, but of determining the nature of the gas. We can tell many things about it. We can tell how hot it is, how dense it is, if it's moving, and what the abundances are within that gas. That's how we know what the sun and other astronomical objects in the sky are made of. Is from the radiation that comes from them. So if we took, for example, the spectra that come from different elements, hydrogen, helium, nitrogen, neon, argon, mercury, they all look significantly different. None of them are the same. In fact, helium was first discovered on the sun, and this is actually an image taken in the helium line from Skylab. And here you can see a huge eruption on the side of the sun. I kind of think of it as a bar chart on something you're taking out of the supermarket. When you scan the bar chart, then you know a lot of information about what you're looking at. Now, of course, these are neutral elements. If these are ionized, then their atomic structure changes a little bit, and these lines will shift a bit. They will be different when the atoms are ionized. So, how many of you here have seen a total eclipse of the sun? Quite a few, yeah? What was it like? Creepy, a little bit scary, a little bit kind of disorientating. Yeah? Did any of you see it here in the UK in 1999? Ah, it was a National Astronomy meeting then, yeah? Or was it in Cornwall, because it was seen in different places in 1999. It is an awesome experience. Even for those we know what's happening. The moon is going in front of the sun, blocking the disk of the sun. But it's awesome because of the eeriness, because of the fact the sun is going out, it's getting dark, it's getting cold. But also it's amazing because this is the only time that we see the solar atmosphere. This is the only time in the visible, we can look at the sun. Because the disk of the sun is 1 million times brighter than this atmosphere, it's the only time you can actually look at the sun. Take the eclipse glasses off, otherwise you won't see anything. And don't forget to take the filter off the camera, otherwise you don't. Even the professionals forget to do that in their excitement, and then they don't get anything. So we are actually seeing the solar atmosphere here. We're seeing the corona. And if you can see, it's very structured. And it's structured because it's ionized and because it traces out the magnetic field of the sun. So you can actually see it tracing out, like iron filings, it's tracing out the magnetic field. It's very beautiful. I'm fortunate to have seen it 3 times, experienced it 3 times. However, it caused a mystery. When the scientists, the observers, astronomers, used a spectrometer to study the sun, they saw some emission lines. These are just emission lines, and one in the green, one in the yellow. This is illustrative, obviously, one in the red. And they couldn't identify these lines. They didn't know what they were due to. It took them a very long time, about 25 years, to actually identify what they were due to. And this is because it was unexpected. They actually invented a new element called coronium because they'd had such a lot of luck with helium, which is named after the sun, Helios, that they thought, well, let's try a new element. That was a scientific theory that didn't really go very far. But in the end, it was some very careful work by Edlen and Grotian in Sweden, in Lund, which enabled them from laboratory measurements to extrapolate along what we call isoelectronic sequences, similar structure of atoms. And they found that actually, for example, the green line is due to iron, which has had 13 electrons stripped off. So normally iron would have 26 electrons. It's got 26 protons in the core, but it's got 13 stripped off. So it's called Fe plus 13 or iron 14, just to confuse, we have two notations. But in order to strip off that number of electrons, you need a very high temperature. So as you heat a plasma of gas, an ionized gas, the atoms the ions bump into each other, and more electrons get stripped off. So it was realized that, in fact, this corona, this atmosphere of the sun that we see during a total eclipse, is actually 1 million degrees. That was very surprising. I'm not sure whether it surprises you, but it's actually very surprising because the surface was only 6,000 degrees. So that's one of the issues, one of the problems, one of the questions we've been trying to address. Why is the solar corona so hot? And we've made a fair amount of progress. I wouldn't say we've answered it completely, but we have made progress over the years. Now, if I go way back in time, for my graduate days, I worked at University College London, and I was very privileged to work with Professor Seaton here, who was a very eminent astronomer, actually president of the Royal Astronomical Society as well. Very kind person as well, very patient. And he gave me a paper when I arrived in the department, which is an eclipse observations from 1952. I was a little bit young then, but in fact, he wanted me to do the atomic physics calculations that could be used to interpret these eclipse data. Now, at that time, there weren't any there weren't any calculations available for these particular coronal lines. The red line is due to iron 10, the iron 14, and other lines. So that was the work that I was given as a graduate student. The group I was in was an atomic physics group. So we did a lot of atomic physics calculations. You have to calculate the structure, then you have to calculate scattering. There's lots of processes that you need to involve. So we're working together with a team of other people who were working on other astronomical objects. Now, working with him at one stage was Dr. Alan Burgess, who did a lot of work on ionization and recombination of atoms. And he was the person that I went to work with in Cambridge. So he was at the Applied Maths department. Sadly, these two people who are very important in my life are no longer with us. This is an eclipse observation taken more recently in the two spectral lines, one for the red line and one the green line. So one is formed about 1 million degrees, the red line, and one is formed at about 2 million degrees. And here you can see the structure again. There are open fields here in the polar regions, and then closed fields where these are these active regions. And you can see different temperature. This is about 1 million degrees, and this is higher at 2 million degrees. As I said, I was fortunate to see the 1999 eclipse with John, my husband, who's my chauffeur tonight, and our children, and it was an awesome experience. But I was also very privileged to be NASA's solar expert at the Great Smoky Mountains National Park. So they had solar experts at all of the national parks and different venues across the USA in 2017. An amazing experience when the eclipse went right across the USA. And we had a morning of celebrations and tense waiting because the clouds began to roll in. And when you're in a mountainous region, once the clouds begin to roll in, basically finished for the day. So we thought, well, we'll have to use the big screens we've got there. But actually it cleared again, and we had a superb view of the total eclipse in 2017. And we had the Cherokee Indians doing storytelling and dancing and other members of NASA and an astronaut as well there with us. Now, it is a bit eerie, and sometimes when people don't know what's going on, they kind of make up stories. And the stories from the folklore of the Cherokee Indians is that when a total eclipse happens, a giant frog is eating the sun. So I was also a little bit nervous and looking behind me to make sure there weren't too many giant frogs around. Now, if you look at the sun in the X-rays rather than in the visible. Now, the spectrum that I talked about the visible, but of course we get spectral lines in all wavelengths, from the ultraviolet to the X-rays, and in the other direction, you can go infrared, and that's what James Webb Space Telescope is doing, studying the spectra in the infrared wavelength ranges and radio, etc. I'm an expert in the ultraviolet and the X-ray spectra. In order to see this, we need to go to space. We need to observe them from space. We can't observe them from Earth. Because that corona, that solar atmosphere, is very hot, it emits very strongly in the ultraviolet and the X-rays. And this is an image, obviously, it's a special camera that can detect X-rays and then colored orange, but this is an image from Yoko, which is an old Japanese X-ray telescope, which was amazing and observed the sun for many decades. And you can see the corona looks very different here. We've got dark regions, which we call coronal holes, where the magnetic field is open and the plasma flows out into space, forming the solar wind, and that forms what we call the fast solar wind. There are regions where the magnetic field is closed, and these are very bright, and underneath there will be the sunspots. So if we look from solar minimum to solar minimum, where there are very few sunspots, to solar maximum, where there are a lot of sunspots, we can see that although the visible light doesn't change very much on the sun, the ultraviolet and the X-ray light changes dramatically. And this, of course, can affect our own environment here on Earth, the Earth's atmosphere. So let me turn to SOHO and tell you a little bit about that, and before I move on to more recent observatories. So SOHO was probably the most comprehensive observatory of the sun that we had. It was operated from Goddard Space Flight Center, where we worked on different instruments, and we worked to coordinate the observations that we were doing. It was launched in 1995, and as I said, it's still operational. So it had 12 instruments which were used to study the solar interior by looking at small vibrations on the solar surface, the solar atmosphere, the corona, and the solar wind that flows off. Now, SOHO actually orbits the sun at the Lagrange point, which is the point of balance between the gravity of the sun and the gravity of the Earth. So it actually goes around the sun with the Earth. It's an unusual orbit, but it enables us to observe the sun 24 hours a day. This is an image from the ultraviolet. This is in a line which is formed at about 2 million degrees from the EIT instrument. And again, you can see the dark regions. So it's colored green because we can't see ultraviolet. We need to color it in order to be able to see it. We have different colors. We like to use different colors. Makes it interesting. We use different colors for different wavelengths, which are sensitive to different temperatures. And I'll come back to that. So you can see these active regions where the sunspots are, but you can see small regions all over the sun. The first impression that I had when I saw this image on a plasma screen for the first time at Goddard was of diamonds sparkling all over the sun. Never seen anything like it. We have instruments which can observe the surface of the sun and measure the magnetic field on the surface of the sun. So this is one of those instruments, a Michelson Doppler interferometer, which is measuring the magnetic field on the surface of the sun. And you can see these are where the active regions are, where the sunspots are. And you can see small little changes, little bipoles all over the solar surface being brought up by the convection zone just beneath the solar surface. This is an image of one of the EIT instrument, the UV, but also superimposed on one LASCO. And LASCO is like a coronagraph. And you can see a coronal hole here, which stretches way down to the equator. Now, when you get a coronal hole that stretches way down to the equator, the magnetic field is open, and as the sun rotates, sometimes that can give you space weather effects here on Earth as well, and geomagnetic storms. So they're quite important features. Hinode was a joint NASA, UK, ESA, Japanese satellite, and it had instruments which were designed to observe the solar surface and the solar atmosphere. So the optical telescope was focused on the solar surface and the magnetic fields. The X-ray instrument was looking at what was happening in the solar atmosphere and the X-rays. And then there was this EUV spectrometer. So that was the instrument that was led by Mullard Space Science Laboratory, University College London, and Louise Hara here was the principal investigator for that instrument. So she led that instrument. And because I'm an expert in spectroscopy, I helped in the design of the instrument in the first place with the scientific objectives, and I was working on the operation of the instrument to decide what scientific results we wanted and needed to get in collaboration with other instruments. A spectrometer is a little bit complex because we have a slit and we need to scan over an image. So rather than getting an image of the whole sun in one go, we have to scan, and this sometimes makes it a little slow. So what we've found is it's always important to combine the results we get from a spectrometer, which are very good and very detailed, with the results that we get from other instruments like an imaging instrument. So at each position along the slit, and for each position we move, we get a spectrum. And this is just a spectrum, an example from 18 to 20 nanometers. In order to interpret the spectrum, and this is a spectrum laid out in a different way, from 170 to 270 angstroms. This is what the instrument produces, what ICE produces. We need to know all of the atomic physics which is producing all of these ions and elements. So you've got lots of different elements. You've got iron, you've got sulfur, you've got neon, magnesium, all sorts of nickel, even though you've all got all sorts of different spectral lines, and it's very complicated to interpret these lines. You need to have atomic data which tells you how these lines are formed at different temperatures, different densities, and use different diagnostics. And that's what I'm an expert in. So here this is a team that we formed called Chianti. We produced an atomic database which could be used to interpret solar and astrophysical data. And this is the team quite a time ago, as you can see, standing on the balcony of our Arcetri Observatory with Galileo's house somewhere in the background. So myself and Julia from Cambridge, our colleagues here from the USA and from Italy. People ask, why did we call it Chianti? Is it an acronym? We did try and think up some acronyms, but we decided that if we called it something nice, then people would tend to use it. And we weren't wrong, because actually this is now universally used by all solar physics people to interpret the data now and to do predictions when they're building future instruments as well. So this is used universally by people, and it's like a black box. They don't have to go into all the gory open heart surgery of finding out individual elements. They can use this and determine the plasma parameters from it. So we keep it up to date. It's all assessed. It's using all the available publications, and it's all input. So everything's there. We guarantee that it's up to date. It's got the most accurate data in it. And we are just about to release a new version. The last version, version 10, was released in 2021. Now, one interesting characteristic using the spectral lines, which I want to mention because it's quite important, is the element abundances in the photosphere of different elements can differ from those in the corona. And this is a phenomena which has taken a lot of understanding. What is happening is where the ions are being formed in that particular region, some of them are accelerated into the solar atmosphere faster than some of them that are still neutral. So it depends on what the ionization potential is for those atoms. If it's very low, then they're already ionized and they're accelerated into the atmosphere. And we can use it as a diagnostic to probe the heating mechanism for the solar atmosphere. And I'll come back to it because it's also used as a tracer for observations with Parker Solar Probe and Solar Orbiter. There are theories which, quite complicated theories, which represent why this has happened, called the ponderomotive force. Doppler shifts. Who's heard of Doppler shifts? I'm sure you've heard of it in other contexts, but in the context of spectral lines, if the plasma is moving and it's emitting, then we can determine the velocity of that plasma. It's a very useful diagnostic if we have the spectral lines. So blue is moving towards us and red is moving away from us. So when we had these observations from Hinode, the EUV imaging spectrometer, we found that there were interesting patterns of downflows in the red and upflows in the blue. Now, this is an active region taken at a particular line at 2 million. That's just the intensity of the lines, but here we've got the Doppler shifts for the lines. And what we think is happening is this is where the magnetic field is opening up and flowing into the solar wind. And this is one of the areas of great research and great interest with Solar Orbiter and Parker Solar Probe. And these observations with Hinode are still being used for that purpose. This shows you what the EUV, the ultraviolet, looks like in solar minimum and what it looks like in solar maximum. And similarly here, solar minimum and solar maximum. So you can see how much brighter the ultraviolet emission is during solar maximum than solar minimum. Another instrument on Solar Dynamics Observatory, more recently launched in 2010, one of the things we've been able to do is to get more and more detail. We call this the spatial resolution. So we've got better and better detail as we get better and better instruments. And this can resolve down to about 1,000 kilometers. So very good pixel size, 1.5 arc-second resolution, and get an image every 12 seconds. So we call that the cadence, how fast we can get these images. And it also has a broad temperature cover, so it has different bands in the ultraviolet. And here you can see from 500 Kelvin at the solar surface, 600 Kelvin, right up through the chromosphere, right up to the corona, right up to solar flares, which goes up to 10 million. And simultaneously, we get these images every 12 seconds in these different temperature bands. Gives us a huge amount of data, a huge amount of information, because we can track the heating and the cooling of different features on the sun. This is what the sun looks like today. So if you go to the Sun Now, Solar Dynamics SDO, you'll see what the sun looks like today from space. So if you're doing any solar observing, you can compare it with what it looks like from space. Now, this is 3 bands at slightly different temperatures, going from the blue one, which is cooler, about just below 1 million, to 2 millions, to just above 2 million, superimposed. So it's actually a sort of temperature map. So the cooler regions are here, where the coronal holes are and the magnetic field is open, and the brighter regions here, where we have the active regions. But you can see all the different filters and different temperatures for those filters. And here's an active region coming into view as the sun spins in one of those wavelength bands. And you can see these huge loops forming, and here is open magnetic field. So if we looked at the magnetic field on the surface and we extrapolated it, we'd see that some regions are open and some regions are closed. So it's a little bit as if we have a bar magnet here, with the sunspots being the foot points where the magnetic field is anchored, magnetic field popping out through the surface, producing these loops in the ultraviolet, very hot loops of plasma. And in the polar regions, where the magnetic field is open, as I said before, that is where the fast solar wind is flowing out continuously. I'm going to introduce you to a concept called magnetic reconnection, because this, we believe, is quite an important phenomena in the heating of the solar corona and other aspects. It's when the magnetic field lines change. So they break and they change their configuration. So when the magnetic field gets very twisted up, it doesn't like to be twisted, so it snaps and it changes its configuration. When this happens, it goes from a high energy state to a low energy state, and magnetic energy is transformed into thermal energy, into heat, or into kinetic energy, into accelerating particles. This can happen on small scales, and we call these nanoflares, or it can happen with huge explosions, which we call solar flares. So if we take one of these loops, these X-ray, you see in the X-ray or the ultraviolet here, it's made up of lots of different strands. Now, beneath the surface, we've got convective motion. These strands are moved around. Now, this is a theory by Parker, Eugene Parker. I'll come back to him in a minute, in 1991. If you stretch out the loop, this is one foot point, this is the other, start off with straight ones, but you move them about, they get twisted up. They don't like to be twisted up, and they reconnect in lots of places. And we call that nanoflare heating. And we've tracked this, we've modeled this, and we've compared it with the observations. And we believe that this is a very important process in transferring energy from beneath the surface up through the magnetic fields and then releasing it as magnetic energy, which then heats the corona. So we believe this process. There are competing processes. Waves could also carry up energy, but that's one process that we're quite keen on. Science is all about debating different people's theories, and the evidence then weighs down on the part of one theory or the other. This is the first visible observation. This is taken by Carrington and Hodgson in 1869, this drawing here, and it's a flare that's seen in the visible. It's very rare to see solar flares in the visible. They have to be very bright. I think he rushed in to tell his wife to come and have a look, and by the time she got there, it had faded a little bit, but he did manage to capture a little drawing of it first. We didn't have X-ray observations at that time, but there were various effects to do with the communication, etc., and aurora reaching right down to low latitudes, which make people believe this is a very big flare. So flares are categorized by the amount of X-ray radiation they give out. They start A, B, C, M for moderate, and X for very large, and it goes 1, 2, 3 up to whatever, 30. This is thought to be a very large flare. Now, a very large flare happening at that time, it was fascinating and people were fascinated by it, but it wasn't very troubling. However, a very large flare happening now in a technological age when we depend so much on satellites and technology is a different kettle of fish. This is an image in the ultraviolet from that satellite trace, and you can see that the flare went off, the loops were twisted, and then afterwards we get these growth of these huge loops. So this is thought to be the sort of model. We get an eruptive prominence leaping off, and then we get the formation of very hot loops that then cool underneath. And we get magnetic reconnection occurring here. We've studied this process in detail from many different aspects. And in fact, one of the instruments that we've used called ARIS, and my student Vanessa Polito has been working on this, looking at the very high temperature emission using a spectrometer, a very good spectrometer that we're able to study many things. We're able to study the chromospheric lines and the transition region between the chromosphere and the corona, and we're able to make very careful determinations of densities and temperatures. I'm not going to go into too much detail because I don't have enough time. This is an illustration. It's a model of an eruption of magnetic field coming up. I'll just see if I can run that one more time. Wait a minute. You can see the magnetic field. maybe if I, no, maybe I can't. I know we can. Anyway, the magnetic field comes up, and then you get it interacting with the overlying fields and then heating, and this is heating the gas. Now, why am I interested in that? These are called jets. So you get magnetic field erupting from beneath the surface into an overlying field. They're quite small on the sun's terms, quite big on our terms. And my student Sargam, one of the Indian girls there, a PhD student, worked on this for her graduate work and produced some models, compared our observations with the models of these jets. But these are actually thought to shoot material into the solar wind. And there's something which people have got very excited about now with Solar Orbiter and Parker Solar Probe. So I'll come back to those. Before I do, I wanted to mention the X-ray wavelength range. We saw those beautiful observations from YOCO, but YOCO was not a spectrometer. The Solar Maximum mission had a spectrometer, which I worked on. And now, more recently, during COVID, when I should have been retired, we got very interested in collaboration with our Indian colleagues who had an X-ray spectrometer, an X-ray instrument on the Chandrayaan-2. You might have heard of Chandrayaan-2. It went to the moon and it had a lander. Sadly, the lander didn't work. They lost communication. They are sending another Chandrayaan up, but it did have an orbiter with several instruments. And one of the instruments was observing the X-ray spectrum from the sun. And you might ask, well, why are we bothering to observe the X-ray spectrum from the sun when we're studying the moon? But it's actually looking at fluorescence of solar light from the moon as well. But it needs to study the sun spectrum to make sure they know what is coming back from the moon, so they can determine the composition of the moon, the element abundances on the moon. But we're really interested in the solar observations, which are the best that we've had. Very, very good observations, working with a team in India, in the physical research laboratory there, that built the instrument. And this gives you an idea of the spectrum. This is down near 1 angstrom. Sometimes you work in KV, but it's in the X-ray wavelength range, and these are for different flares of different magnitude. So we've got a quiet sun, more active region, bigger flare, C-class flare, and then M-class flare. So for different flares, the X-ray intensity gets bigger, but we can see very small features. And we can see features which correspond to the different elements. And from this, we're able to determine element abundances and other parameters of the plasma that's emitting here. Now, I've not got time to go into the details, but one of the things we find is that during a solar flare, during the initial stages of a solar flare, we believe the reconnection happens up here, and that heat energy is transferred shooting down to the foot point regions, and then material from the chromosphere evaporates up. So what we find is that we start off with coronal abundances because the loops are filled with coronal material. When we get the particles and the heat shooting down and we get chromospheric evaporation from the photosphere, the abundances go down to photospheric values down here, and then they recover again. So as the temperature goes up, it comes down again, the abundances drop and go back again. So it's clear evidence for the model in which energy is transferred down into the foot points of these loops. So very excited about this work and have published more papers than I published in the last decade, I think. My husband's a bit annoyed about it, but there we go. And we have, one of the advantages of lockdown is that we've had weekly Zooms with our colleagues who have young, very enthusiastic students working with them who can handle all the software, and both have just completed their PhDs. So this is a simulated eclipse. It's called a coronagraph, and this is from LASCO. So we've blocked out the sun here. This enables us to see the very faint emission coming from the sun. So we can get billions of tons of material moving at very high speeds from the sun. And here's an example of something erupting here, and then you'll see an injection into space. Here's it from a larger distance. Here's the sun, and here's an eruption, and you can see how far out these coronal mass ejections, these massive amounts of material, shoot into space. Now, of course, we're interested in them, but perhaps not necessarily so interested if they're not coming towards us. We're interested in the process which triggers them. We're interested in how they propagate. But we also believe they contribute to the solar wind. And the solar wind is what impacts on the Earth and gives us the geomagnetic storms. So let me step back a little bit and think about the solar wind a little bit more. Comets, I'm sure you're familiar, and I'm sure you've got photos that you've had of comets over time, but they have two tails, and one is a neutral tail, the blue tail is the iron tail, and that follows the magnetic field, and the other is the neutral tail. So it was in 1910 that Eddington suggested the existence of a solar wind, electrons streaming off the sun, which caused this differentiation in the comet's tail. Eugene Parker, again, in 1957, studied the solar wind, and he did some models which predicted how the solar wind evaporates from the solar surface. Now, a little bit like Galileo, nobody believed him at that time. They didn't think this was possible. He wrote a mathematical paper about how this was done. What we do when we write a paper is it goes out to referees in the field who are knowledgeable in the field, and they decide, whether it's valid or whether they believe it. They do a lot of work, and then they send you a referee's report. This went out to 2 referees, and it was rejected by both of them because it was going against common knowledge, or what they thought was common knowledge. Chandrasekhar, again, a very famous astronomer, overruled them. He was the editor of Astrophysical Journal, and he overruled them, and he said there is nothing wrong in the mathematics in this paper. So he published it. Now, this paper by Parker is now a seminal work in the field. It is the reference or the starting point for all studies of the solar wind. And that and his work on coronal heating is the reason why he was honored by having Parker Solar Probe named after him. So this is quite a complicated diagram here. It's actually data from the Ulysses satellite, which actually samples the solar wind. And it flew over the polar regions, 2 orbits, I think, but its radial velocity, the velocity is, of the solar wind is plotted in a radial way. So this is the steady, the fast solar wind. But when it comes to the equatorial regions, where we have these active regions, it gets much more intermittent and dynamic. The speed is around about 700 to 800 kilometers for the steady fast wind, which is constantly blowing. But when we get to these regions down here, it can be very variable, and the abundances change, the ionization stages, everything changes very rapidly. And it's this part that the scientists have focused on recently. We understand quite well the fast solar wind. In fact, I did some work on SOHO, which showed where it was coming from. But this is important because it can cause shock waves in transit from the sun to the Earth, and it can impact quite suddenly on the Earth, and that's what causes the geomagnetic storms. So we've got the 3 different areas. We've got the coronal hole with the fast, steady solar wind. We've got coronal mass ejections, which I showed you, which shoot out into space, which can be observed in the solar wind. And then we've got a slow but very intermittent, very spurty wind, which comes from these active regions. And it's that which people have been focusing on and trying to understand. Of course, when the solar wind impinges on, this is illustrative of, not to scale, hasten to add, of the Earth and the sun, it is protected by its own magnetic field. And it's got this magnetic sheath around it. But the wind can impact quite suddenly, depending on the direction, its magnetized direction of the magnetic field. And it can cause the magnetic field on the Earth to change its structure and reconnect on the night side of the Earth, and then particles, when it reconnects, that same process of magnetic reconnection, particles shoot down into the polar regions, causing the aurora. If it's very intense, then the aurora can spread further down these magnetic field lines. It causes beautiful effects. The aurora, this is seen from the International Space Station, but it also causes harmful effects. It can harm astronauts if they're in space, can damage satellites, it can completely knock them out, it can cause electricity blackouts by inducing large currents in the electricity cables, and it has done all of these things. There are mitigating circumstances in which you can put a satellite into a safe mode. It also affects flights going over the polar regions. It's number 4 on the UK risk register. Okay, that doesn't mean it's a risk to life. It means it's an economic risk. So there's a huge amount of work going on in regard of what we call space weather, and that is the effect that the sun has on the Earth. And now the Met Office, which traditionally has worked on weather forecasting, now has a whole section dedicated to space weather forecasting, right from the origins of what's happening on the sun to how it's transported to how it impinges on the Earth. So Parker Solar Probe launched in 2018, and here is Eugene Parker. Although it was delayed by a day, he was able to watch the launch of his own satellite. Now that was unique. Normally satellites are named after people who have passed away. Sadly, Eugene Parker has now passed away, but he did have the pleasure of watching it. And this is Nikki Fox here, who is the principal investigator on Parker Solar Probe. It's in an unusual orbit, which has to bring it closer and closer to the sun, using Venus as a slingshot. It has already got very close to the sun and entered the environment of the corona, let's say. It doesn't actually have instruments which observe the sun as such, but it does have an instrument which observes the gas that flows off the sun very close. It's used to detect lots of different things. It's got lots of different instruments there: protons, waves, energetic particles. It samples the sun. Of course, it has to have a heat shield because it goes so close to the sun, and that was technologically very challenging to develop. It also has to be automated because when it goes around the back of the sun, you can't communicate with it, and it has to keep pointing at the heat shield at the sun, otherwise it would just burn up. So Solar Orbiter was launched in 10th of February 2020. Now, I'm not sure if you remember February 2020, but it was quite an unusual month, followed by March, which was even worse. It had a very successful launch, a beautiful launch, but then suddenly everybody was down in lockdown. So basically, Solar Orbiter had to be tested and guided from home screens, from using in Germany was ESA was the main player. Of course, they had the computers and they probably had 1 or 2 people in there, but they had to liaise and they had to point the cameras at the computers because there was a security issue as well with just plugging your computer into the computers that were guiding Solar Orbiter. It was an amazing feat for the ESA and NASA engineers and technicians to test it. We call that the commissioning phase. But it all worked according to plan and was all done on time. And the science instruments were all operated and tested according to plan. I think that in itself is just an amazing feat. It has a 10-year mission. The cruise phase, as I said initially when it was tested, but now it's in its science phase, and it has been close to the sun. It can't transmit data all of the time. It transmits data when it gets back to the Earth, so it has to store the data, but it has had some quite close passes to the sun. It has 4 instruments, which we call in situ, which are sampling the solar wind, but it also has 6 instruments which are observing the sun. We call those remote sensing. So if we compare Parker Solar Probe and Solar Orbiter, Parker Solar Probe stays in the ecliptic plane. Solar Orbiter goes out of the ecliptic plane gradually as it orbits. It also uses Venus as a slingshot, and it will be able to see the polar regions, the solar polar regions. Parker Solar Probe goes very close to the sun, 0.05, 0.046 of an AU. That's the distance between the sun and the Earth. And it has mainly in situ measurements with one instrument which can observe the solar wind. In contrast, Solar Orbiter goes close to the sun, but not as close. It goes to 0.28 AU. It's already been to 5 AU. It's always 0.5 AU. It's been closer in, I think, to 0.35 now. But it has instruments both that sample the solar wind and also in situ. So quickly, because I know I'm running out of time, what results have we had so far? Well, those little solar jets that I was talking about that my student Sargan worked on, the first thing that they saw is something called switchbacks in the magnetic field. They saw regions where the magnetic field did a Z, far more than they've ever seen before, a magnetic field like this. And they believe that those are caused by these jets interacting with the open field and then producing these little switchback regions. So they believe that it's showing you the origin of the solar wind on the solar surface. Some people argue that these could develop during the solar wind as it progresses, but I think that the evidence now suggests that it's actually originating on the solar surface. It's one interesting observation. There was a link to one of those equatorial coronal holes that I talked about, which they found directly, and a lot of people are now working on linking what we see on the source of the sun with linking what is seen or sampled in the solar wind. An interesting result from the UV instrument, the EUI imaging instrument, very, very detailed observations of the sun, more than we've ever had before, the amount of detail, spatial resolution down to 800 kilometers when it's at 0.5 AU. Very, very detailed. And they see these little bright points. I mentioned the diamonds that I saw from Soho. They're observing these all over the sun. And these, they believe they call them campfires. Interesting name, always catches the press. But anyway, I think they're what we saw with Soho. But they're little heating points all over the sun. And there's a great deal of study now going into those, understanding them and modeling them. Now, what I didn't say was that Solar Orbiter also has a spectrometer on it, which of course is close to my heart and what I'm interested in. So what can we do with a spectrometer on Solar Orbiter? This has been built by the Rutherford Appleton Laboratory in Didcot and is now also the principal investigator team is now in France, in Paris. We can determine all the elements that are in a particular region. So a small region like that, that's a spectrum, and it shows you all the elements, the temperatures, the densities, all the rest of it. But we can sample the elements. Now, this is a sample of the elements taken with one of the other instruments, the SWA, Solar Wind Analyzer, and it's got the element abundances there. It's as if you put a dye of ink into a flow of water. The element abundances don't change. The other parameters like the densities or temperatures might change as the solar wind goes, but the element abundances stay there and you're able to track back. So there's a lot of great interest now in determining the element abundances on the surface of the sun and linking them through to the solar wind. That's just two examples that I give you of results that are beginning, amazing results that are beginning to come out from Parker Solar Probe and Solar Orbiter, being used in conjunction with other instruments like HINODI, the Solar Dynamics Observatory. It's important to also get the context. What's happening to the solar sunspot number now? This is 1990 up to 2030, so we're around here somewhere, and you can see the sunspot number is going up quite quickly. So this solar cycle is expected to be a little higher than cycle 24, and it will peak around about 2025, so in a couple of years' time. So if you haven't yet seen the aurora, I suggest you begin to book your tickets now, because this is a good time as the solar cycle rises to be able to see aurora. One instrument, an X-ray instrument on solar orbiter, is observing solar flares. We've observed X-class flares with this instrument. It's a hard X-ray instrument. We're able to get high temperatures and particle acceleration from it. And we're combining these results with the results we're getting working with the group in India. And we're now combining the two sets of observations to get the best information we can. Here's an image taken from solar orbiter of a coronal mass ejection coming from the sun. So finally, I work a lot with India. I've mentioned India a lot. I work with the group at the Physical Research Laboratory in Ahmedabad, but I've also worked for a very long time with a group, IUCA in Pune, where Durgesh Tripathi here is our professor. He heads that group. He did work in my group in Cambridge. And Sargam here was my PhD student, but I worked with a lot of the young researchers there. I was over there in February this year to visit them and to work with them. It's very exciting to work with them. They have their very own, ISRO is the Indian Space Research Organization, and they have their very own first mission to the sun called Aditya L1, which will be launched later this year. And it has several different instruments on it to look at the solar surface and to look at other aspects. And it will be at L1, which is the point where SOHO was. I also work a lot with schools, and here you can see I'm demonstrating some things to the schools. So there's different instruments there. I won't go into the detail because I'm running out of time, but that should be very exciting, so watch out. Now, in the introduction, Jerry mentioned that I work on sun space art. I lead a team of scientists and artists who work together, engaging mostly younger children in primary schools, but also older children with solar topics, space topics, with solar system topics. So we have a science engagement, and then we do some work, creative work in different aspects, working with visual artists. So I have a team of 15 people, some scientists, some professional artists working with me. This is an example. This is this is flags of the solar system, an example of a school, and they produced their interpretation of different planets, etc. And we get them to, on the back, we write some facts and things about the planets. It's funded by SDFC, for whom I'm very grateful, because they actually support this link between the science and the arts. We also do drop-in activities at festivals, and we were at Cheltenham Science Festival last week, running some activities with the schools that came to that. And yesterday I was down in London at Queen Mary College running some activities with schools from the East End of London. We try to engage with children who perhaps haven't had the opportunity to engage with scientists or astronomy, because astronomy excites children, and you've found this, I'm sure, in any outreach work you do. It's exciting for the children, and we use it as a starting point. So thank you very much for your attention. That's the end.
Thank you very much, Helen. And I realized actually quite early on that part of my introduction was incorrect, that you weren't going to, we weren't going to learn more about the sun than we had before. Although that was true, we were going to learn more about the exploration of the sun than we ever knew before. Right, we're going to take questions. First of all, does anybody in the room want to ask a question? Just raise your hand first, please. Okay, can we get a...
We're gonna have to repeat the question.
Okay. All right.
You showed that sequence of the solar flare going out. Goodness knows how many millions of miles. It's really amazing. It made me think,
If it was coming straight at us, would we get that same sense of how big it is? In other words, if I'm staying on a railway line, I can see a train coming, but I don't know how long it is. Is that a sort of problem that you're facing? Would that be a problem that you face in that situation?
Okay, so the question is about if there is a flare shooting out from the sun, if it's actually coming towards us, can we tell its size or volume, perhaps? Really, that's basically it.
Yes, we can, definitely. In fact, Soho, because Soho is between the Earth and the sun, I didn't mention it, but you get a phenomenon called a halo CME. So it just expands out and it hits Soho first, and what you see is a lot of like a snowstorm. Little particles are actually hitting the Soho. But of course, yeah, we can tell it's coming towards us, and we can measure it. But there are other instruments. We want to know how fast it's moving. There are other parameters, and that's not always possible just by seeing something expanding towards you. So there are plans, for example, for ESA to have a satellite at what we call the L5 point, which looks kind of perpendicular to the Sun-Earth path. And then you can actually see how fast it is moving. With stereo, it was possible to judge how fast it was moving because you've got two satellites, so you can get a three-dimensional image. But it's quite important to know how much material there is coming towards you, obviously, but also how fast it's moving.
Thank you.
There's a question that's come in on Zoom from Alan about coronal mass ejections. Usually when we hear about them, it's along the lines of these are bad for us. So his question is what steps are taken to provide any kind of protection?
Yeah, they're bad for us because they'll hit the Earth's environment, that magnetic protection. And we can take steps. So if there is a space weather warning, in a sense, the space weather has to categorize, it goes from green to orange to red, So you have to judge how serious the risk is by how fast it's coming, what the magnetic field direction is, and how much material, etc. Then, for example, satellites can be put into a safe mode. So you could put them into a safe mode, which would minimum amount of damage, but that costs money to do that because that satellite won't be operating. If you're flying over the poles, you don't have to fly over the poles. You could go by a route, but it would be longer. So again, that costs money if you want to do that. With the electricity grids, I understand an awful lot of work in this country has been done by the electricity grids to see if you can reroute. The main problem with electricity is that transformers are blown and then it overloads on other circuits. So and it takes a long time to repair and replace a transformer. So what you can do is reroute and have the possibility to bring on more transformers or more routes. But again, that's costs money, it's economic. So there are mitigating activities, and they've been studied in great detail by commercial companies and by electricity grids, etc., to see what can be done. It's interesting to note that between Apollo 16 and Apollo 17, when the astronauts were not on the moon, fortunately, there was a very large solar flare. Had that happened when the astronauts were on the moon, and they wouldn't have been protected, they would have got a massive dose of radiation, which could even have killed them. So it's a big problem for space travel as well, how to deal with not just the solar radiation or cosmic rays, but also the cosmic rays coming from space. And it's one of the biggest technological problems for space travel.
And indeed, that's something that the Artemis project is going to have to look at as well. Okay, we have another question from Richard Shepherd, talking about the effect on iron. So 26 electrons, half of them get lost. He's basically asking, what happens to those electrons?
Yes, when you've got an atom and you've got atomic structure with a nucleus, with 26 protons and neutrons, and then you've got electrons around the outside, what happens is you form a plasma. So those electrons are basically freed. So they're running free in the plasma. They can then knock into other ions and atoms. So you're left just with an atomic structure which has the 13 electrons attached. We can heat it more, and during a solar flare we can strip it right down to 2 or 3 electrons. So you can see even iron 26. So you can strip it right down, but it has to be more energetic to do that. So basically, yes, the electrons are freed, and then you have positive ions and then free electrons. It's called a plasma.
Okay, so there's a related question which hit me hard when I saw what you put up on the screen. 26 electrons, half of them go, and you get what is referred to as Fe plus 13, or
FeX1b.
Fe14.
Yeah.
And
Why?
yes.
Yeah, okay, that's a good question.
I was going to say, if the answer to that is don't ask.
No,
then I'll
it's a good question. It's a matter of languages. Fe plus 13 is the way that atomic physics people do it. FeX1b is the way that people analyzing spectroscopy do it. So you have different languages have developed in different areas of science, and then you have to kind of combine them together in a diplomatic way. So it's yes, spectroscopists that did the laboratory spectroscopists would have used the Roman numerals, whereas others have tended to use the plus 13. I should have said, with regard to the electrons escaping, of course, iron's composition, the amount of iron in the solar corona is very, very small. We're talking about 10 to the minus, very small compared to the amount of hydrogen and helium. So actually, those electrons are not contributing very much to the overall number of electrons and protons that are there.
Okay. Any more questions from within the room? Yes.
The sun has a polar reversal every 11 years, so its full cycle is 22 years. Yes. Is it a sudden transition, or is it a gradual transition from that? And is there a correlation between the speed of rotation and the peak of sunspot? Okay, so the sun polar alignment effectively swaps every 11 years. So the solar cycle really is 22 years. So the question is, how long does that swap take? And the second part, just what in terms of the speed of rotation,
right?
Does it relate to the peak of solar sunspot?
Yeah. Okay.
Okay. As the gentleman said, what happens is at one stage, the sun has a dipole with a north pole and a south pole, a bit like the Earth's magnetic field. And then that swaps over. So you end up with the south pole up the top and the north pole down the bottom. And then it reverses again with the north pole at the top and the south pole. So it's actually a 22-year cycle from north-south to south-north to north-south. And when it does that transition, it goes through multiple stages. So it's no longer a dipole, simple one. It's got through multiple stages. Now, the transition obviously takes about 11 years, and that's when you get the active regions and all the rest of it forming. But people watch out for the first sign of a transition or the beginnings of a transition. So they'll begin to watch very carefully the magnetic field. I'm not sure exactly how long it takes, but obviously the cycle itself takes 11 years to do that transformation into multipole. Now, the other question was, does it depend on the speed? Now, the actual reason why it's 11 years it's not well understood by me. I'm not a specialist, but it's apparently not understood by people who are specialists. But the way in which this is being tackled is by looking at other stars that also have similar activity cycles, but on different scales, different number of years. And they can also measure the rotation rate. There's quite a lot of work in that field of helioseismology to put the sun in the context of other stars and see what is causing that exactly 11-year cycle.
Richard has a follow-up to his question about coronal mass ejections.
Alan.
Oh, it's from Alan, isn't it? Sorry. And their impact on Earth. 30 years from now, we're all driving around in electric cars. Is that going to be a problem?
Yeah, of course it's a problem. I mean, my husband and I, John and I, were in Italy once, weren't we, when we had an electricity blackout in the whole of the north of Italy. I think it was to do with electricity being transferred through from Switzerland or somewhere, and one of the links had broken and the other was overloaded, and it just knocked out. Well, we couldn't move anywhere. We couldn't. The petrol pumps, petrol pumps don't work. The trains. I mean, for heaven's sake, the cappuccino machines didn't work either. Absolute disaster. We were trying to get a flight at the time. We did eventually get a taxi, but they couldn't fill up with petrol. We were trying to get to the airport. Yes, electric cars. I mean, I'm sure that the people will work on this problem, as they have done already. They put a lot of effort into making sure there are alternative sources of energy if one of the transmissions goes down or one of the transformers is blown. But of course, it's a problem, particularly for a large area. And I think the whole of Quebec once was knocked out by a solar storm in the 60s. Yes, so it does happen. But of course, their pipelines are their electricity pipelines or whatever is induced, are much longer than ours on east-west as well.
Right. Any other questions from within the room?
One of them, you mentioned one of the probes can go behind the sun, and obviously there's a gap between it and the sun. What's the closest we could actually get before it actually is finished?
Okay, so the question is about probes going behind the sun and how close can they get to the sun, basically, and survive. Yes.
Yes, so they go, both Solar Orbiter and Parker Solar Probe go behind the sun, so they're in an orbit that goes around the Earth and around the sun. And as I said, they use Venus as a slingshot. So Parker Solar Probe goes very close. It goes to 0.046 AU. Now, perhaps someone can work that out in kilometers. That's like 5% of the distance between the sun and the Earth. It's very close, but it does have this heat shield made out of carbon composites. But that's why Parker Probe goes so close. It doesn't have any holes that the instruments look through to look at the sun. The Solar Orbiter doesn't go quite as close as that, and it has some hole. It is able to look at the sun if the gates are lifted and it looks at the sun. But one of the things I was pointing out about going behind the sun is the sun produces a lot of radio emission, so it's very difficult. You can't communicate with the satellites when they go behind the sun. So what they did is cross their fingers, okay? So when it goes behind the sun, and then when it gets round, it goes beep, we've made it. So they're all sitting there, very tense, waiting for the beep to tell it we're okay. We've managed to survive going behind the sun. But obviously, for anybody involved in a space mission, which have put that much effort and money into it, it's a very tense time.
It's a bit like on the Apollo program that when the astronauts went out and went behind the moon for the first time, they fired the engine to slow them down to get them into orbit whilst going around the far side of the moon. And they're working out in mission control when they're working on the flight path. How are we going to tell that they've got it into the orbit at the appropriate position? And they realized it was when they reacquired the radio contact. If the engine had fired for too long, then it would take longer before they got into contact. Whereas if it came up early, then they'd know that they hadn't fired for long enough. So it was when that they got that reacquisition of signal that they could tell precisely the orbital characteristics. It worked the other way as well, because on Apollo 8, the astronauts, they knew that this was going to happen, and they said, we're going to go behind the moon and lose the signal. And we also need to know that we are the right distance from the moon, and therefore that will tell us at what time that loss of signal should take place. And one of them said, suppose they just say, oh, this is the time, let's turn it off. And well, I said, yeah, I could just imagine Chris Kraft doing that. Anyway,
say one more thing, Jerry. I've brought some handouts there. There's some posters of Solar Orbiter, and there's a few books about it and some stickers and things like that. Please help yourself. If you've got anything left, Jerry, just take it to one of your things and give them away.
We'll do that. We'll take it to one of the observatory's open evenings that we help out at. Well, Helen, it is, as I said, it would be a very interesting evening. We really enjoyed it. Thank you so much for coming along and providing a highlight to the end of our program for this year.
Well, thank you very much for inviting me. Thank you, everybody.
So there is coming up the Week Hampstead Open Day. Also, there's the Royal Astronomical Society's annual picnic in Greenwich Park, which is great fun. Anybody interested in that, see me afterwards. But now I'm going to hand back to Alan. So over to you, Alan.
I would like to repeat those sincere thanks to Helen for coming down and giving us that absolutely terrific talk. Helen, I hope that you and your husband have a very safe journey back home and take the warm thoughts of our group with you. We have, to the rest of you, everyone who's in the university and on Zoom, to remind you that we have our next meeting, our next full meeting on the 6th of September, Wednesday the 6th, when our President Roger O'Brien will be talking about the Starship project. Before that, the Saturday before that, as a tradition, we have an event in Welwyn Garden City to help promote the club and get people interested in it. And we'll keep you informed about that and any other events through our regular newsletter. Also, between now and September, it's the time for renewals. So we will be sending renewal notices out with our newsletters, just to remind you that we're still here and it's better to do it earlier rather than later. Other than that, all I'd like to say, one last quick thing. Just before you go, Helen, we have our own space artist in the audience in front of you, in the front row there. I don't know if you've got a time just to say hello to him, but he does some pretty phenomenal work as well. So
Helen,
going,
I'm afraid she's gone.
she's gone. Okay. Oh, sorry about that, Martin. I was trying to give you a little plug there. Okay. So to all of you, university and on Zoom, I'd like to say have a wonderful solstice, and I look forward to seeing your pictures on television at Stonehenge. So for now, goodbye.